Alright, today we're going to talk about energy changes within chemical reactions. We're going to look at two different types of chemical reactions, one that absorbs energy and one that gives off energy. We're going to start with a reaction between hydrochloric acid and NaOH, sodium hydroxide. Okay. Now there's a movie of this, and you should have seen this before we started talking about it. But this reaction is a double displacement reaction, and it goes to NaCl plus H2O. Okay. But if we were to use your crazy net ionic skills, what you'd see is that all of this is aqueous except for water, which is liquid. And we know at this point that these guys are spectators, and that means that they cancel out when you look at the net ionic equation. So that means I can ignore the sodium and I can ignore the chloride, right? And then I will get a net ionic equation that looks like this. H plus OH minus goes to H2O. Okay. And what's important about this reaction for our standpoint is that what's happening is that we're forming a bond. Okay, we're forming a bond. And forming a bond means that two particles are coming together. And there's actually no difference between two molecules or atoms coming together and two planets coming together, or a rock simply falling towards the earth. What's happening is that two particles are being attracted, right? It means that two particles are attracted. And when two particles attract, right, it's the same as having like a rock falling towards the earth. If it falls downward, it releases energy. Anybody who's ever had something fall on them knows that it releases energy, right? Like water falling down a waterfall, a rock falling to the earth, right? It releases energy as it falls downward, okay? And that's because what's happening is that the earth and the rock are attracted. Okay. And so when particles are attracted and they move in the direction of that attraction, they release energy. Okay. And so forming a bond is going to give off energy. And you see this in the video of that reaction by the fact that the hydrochloric acid and the HCl start out at room temperature. Right. And then what happens is when they react, right, they give off energy and they become NaCl and water. And what happens is, as it goes downward, as the energy goes downward, right, then as you change energy from HCl and NaOH, which is higher in energy, right, to NaCl plus H2O, which is lower in energy, right, the reaction has to release energy. Okay, and as it forms bonds. Right. And that release in energy we see because it gave off heat. The water gets warmer. In the case of this reaction, you saw it get warmer and went from 25 degrees to about 40 degrees. Now, if we were to actually draw it out, we always draw it as if it follows a curve like this, as if the reaction follows a curve like this, where you start at reactants and go to products and it releases some energy. But there's some energy of activation that we have to put in, to get the reaction to start. Every reaction requires some activation energy, and we always draw it in as if there's a curve going up and then falling downward. But the important thing from our standpoint today is this downward drop in energy causing by a release in energy to the surroundings, and what that meant was that we saw it because it released energy and the water around it, around the reaction, got warmer. Okay, and so we can see this reaction give off energy. Okay, now this is a weird drawing of it, but this is the drawing that chemists use, where we draw reactants and products and show the change as either a positive change or a negative change. In this case, we say that the energy change is negative, right? We say that the energy change is negative. We say it gives off heat, or we say that it is exothermic. Those are three ways of saying the same thing. The energy change is negative, it gives off heat, or it's exothermic. And I like this word exothermic because exo, right, like exit means leaving. In other words, heat is leaving the system. Okay? And that's why it got warm. Now you can probably think of other exothermic reactions. Any reaction that gives off heat is exothermic. This is one, though, that I like because you can connect it directly to the formation of a bond, because the only thing that's happening here is the formation of that bond between H and OH minus. And so as H and OH minus get together and form the water that's no longer breaking apart, it releases a bunch of energy, and we see that in the water getting warmer. Okay? And so that's an exothermic reaction. We can do the same thing when we have an endothermic process. The difference, though, is in this case, an endothermic reaction, and this looks a little bit like into, right, which means absorbing, right? It looks a little bit like into, which means absorbing heat in this case, absorbing heat. If we have an endothermic process, that just means that the reactants are much lower than the products, and that we have the same process, but instead the reactants have to go up to get to the products. And that means that they have to absorb heat. Now, the example you saw in the video was of ammonium chloride, and we had NH4Cl, and it was a solid. And then it dissolved, and it became NH4 plus, right, plus Cl minus, aqueous and aqueous. Okay, and so what's important about that is that we see that we have a very simple reaction involving the breaking of a bond. Right? And that breaking of the bond causes it to absorb energy. Right? And that's why the water got colder. It went from like 25 degrees to around 17 degrees. And so when you absorb energy, when you break bonds, you absorb energy. And that kind of makes sense even with our Earth rock model. If we have the Earth, and we have a rock on it, then it takes energy, right? It requires energy to lift it. Right? That means that when you separate two particles, like a rock and the earth, you're adding energy to the system, right? You're adding energy to the system. And so we're separating these two particles and allowing them to drift around independently. And so we're breaking that bond, and that requires us to separate them, like stretching a spring or lifting a rock away from the earth. And so it absorbs energy. And the way we see that absorbing of energy is that the water around it got colder. Okay, because it was absorbed. Okay, so these are two types of chemical reactions, and what we really need to get your head around for this is that there are two processes that we've really talked about. We talked about something that's exothermic, right? And we need you to know the term, and endothermic. We need you to know that term. We've talked about how this means that it's absorbing heat, provided we're endothermic. Let's try it again. It means we've talked about that it was releasing heat. Shame on me. Or we've talked about that this means absorbing heat. Further, we've talked about how this lowers the temperature. Of the surroundings, and this one would raises the temperature of the surroundings. We've talked about how this one involves breaking bonds. And this one requires the formation of bonds, or the net formation of bonds, right? Right. We've talked about how this looks like a net drop in energy. Or, I'm sorry, the energy of the system rises. Right, and it looks something like this when we graph it out, where we have reactants and products. And then over here, the energy of the system decreases. And that looks something like this. Okay, with reactants and products. Now that's a lot of information, but you can probably connect it to reactions that you've seen, right? You can probably connect it to burning. Right? Burning gas in a Bunsen burner, or melting ice, right? Or maybe using a cold pack or something like that, or possibly I can think of physical changes easily. But let's just take these two for a moment and see if we can't classify them. Right. right? And so let's just take these two characteristics of them and see if we can't identify them. Well, with melting ice, you know that it feels cold, okay? Right? With burning gas in a Bunsen burner, we know it feels hot, although you probably shouldn't have felt it. That would be dangerous. But you know it gives off heat because we use it to boil water and things. So if that's true, that must mean that this one is exothermic. Right? And that must mean that this one is endothermic. Right? But along with it, because we know it's exothermic and because we know it's endothermic, the other one is endothermic, we know that this one must involve bond formation. It's hard to see how burning involves bond formation, but it turns out that forming CO2 and forming H2O release a lot of energy, right? So making those two releases a lot of energy, and in fact it releases more than the breaking apart of the methane. And so it involves, what we're going to say involves net bond formation. And that just means more or stronger bonds form than the bonds that break, right? So it's going to involve bond formation. Melting ice is easier because you can see a solid breaking apart to form a liquid, and this must mean that it involves net bond breaking. Right? And some endothermic processes also form some bonds, but it means that the bonds that break are either more bonds or stronger bonds that break. Okay? Well, that covers everything in this part of the class. On Monday, we're going to do a couple examples here in class, and you'll get to take observations and classify them. Then on Tuesday, you're going to use the data from Monday's class on an RQA. Okay, so our schedule is this: on Monday, we're going to do lab where we take data that we're going to use the next day in the RQA. And on Tuesday, we'll have an RQA, right? A quarterly assessment where we're going to use the data we took on Monday. Now, you have no homework over the weekend, but you need to, if you haven't finished tasks 1 through 3 on the RFP, you need to make sure you finish tasks 1 through 3 on the RFP. All right? Thanks.